Hello, thank you very much for the organizers for organizing such a great workshop. So I'm going to talk about, I'm also going to talk about correcting errors, like Amos did, but in a slightly different framework. So I'm back to the question that Ran talked about, and I believe Allison in the beginning of this workshop talked about, which is the question of interactive coding. This is joint work with Zvika Brakersky. And I'm going to show you, the goal is to show an efficient, computationally efficient, so polynomial-time interactive coding scheme that is resilient to adversarial noise. Okay. So let me explain what this is. But since we're in Paris, I thought, it's only fair to start with a love story. And actually, before we go to the interactive coding, let's first start with just one-way encoding. So back to Shannon's original problem. So here we have Alice and Bob. And Bob wants to send a love letter to Alice. But of course, he's afraid that some error may occur. What do? Well, we apply an error-correcting code. So this is a beautiful theory that was invented in the 40s by Shannon. And by now, the definition, what is a good, so actually before that, there's two error models that were considered and are largely considered today. One is the stochastic error model, where just errors are assumed to be random. Each bit is flipped with probability p, an error occurs, otherwise doesn't. That's the stochastic model. And then the adversarial model doesn't want to make any assumptions. And we don't know when errors occur, when we're not. We don't want to make any assumption. The only assumption we're making is that the number of errors is somehow bounded. So not everything is errored, but some epsilon fraction is errored. Okay? So we call this the adversarial model. And the model we'll consider today is this model. Okay? So errors happen. Some bits are flipped. We make no assumption on which bits are flipped. The only assumption we make is that some constant fraction of these bits are flipped. So some bound on the total number of bits. Okay. So what properties do we want from error correcting codes? So by now there's tons of work in the literature on this topic. And what we want, there's this notion of a good error correcting code. And the properties we want from a good code is, first, we want it to be resilient to constant fraction of adversarial error. So we want to be able to correct even if some 0.1 of the entire bits are flipped. We want only a constant blow up in communication. So we don't want to take a short message and make it gigantic. We want to blow up the size by only a constant. And we want the encoding procedure and the decoding procedure to be computationally efficient. And what do I mean by computationally efficient? We want it to be polynomial time. So you take a message, the time it takes to encode is polynomial, the message size, and likewise to decode the message. Okay? This is a good error correcting code. Okay. Now we're going to our setting. So, we started with the love story. Hopefully, this love story continues. And, Alice sends, a love letter back to Bob. And hopefully this relationship, goes on, and they talk for a long time. And now we want to be able to correct errors in this long conversation. Okay? So we want to take a way to, instead of talking in this protocol, we wanted to convert it into what's called an error-resilient protocol. In the error-resilient protocol, so the messages are slightly different. They're kind of encoded. And the property we want is exactly as before. We want to say, even if there's some error somewhere, so epsilon fraction, 0.1 of the bits anywhere here are flipped, I still want to be able to decode the original conversation. That's the goal. And so these are the desired properties. We want to take any protocol, convert it into an error-resilient protocol. We want it here to be resilient to constant fraction of adversarial error. So we don't know where the error happened. Maybe both these messages were completely lost because, we were in a, I don't know, we talked and I went into some underground, subway. And so I don't know where the error happened. It happened somewhere. As long as only some small fraction I want to be able to decode. I don't want to talk too much longer, so I want the blow-up in communication still to be only constant. and I want to be efficient. What do I mean by efficient or efficiency preserving? Which means if Alice and Bob, their time, they ran in time t throughout this protocol, I want them here to run in time like poly in t. So I don't want now the encoding and decoding procedure to make them inefficient. Okay, so I want to preserve their computational efficiency. Okay? And okay, so this is the problem of interactive coding, which was initiated, proposed by Schulman in 92 and 93. And this is what we're gonna show. So what we're gonna show now is interactive code, like a good interactive coding scheme. So the analog of a good error correcting code. Okay, questions before I show related work and go into the actual scheme? No. Okay. So first, let me just mention one for those who are not familiar with this topic. One may first think, why doesn't the trivial idea work, which is just, why don't you just apply in like Shannon's error correcting code to each message separately? And the reason why this doesn't work is twofold. First, it's clearly not secure for adversarial error, because if this entire thing is corrupted, there's no way to recover it. Okay? But I just want to say that even for random error, this doesn't work, because if here you have only one bit, and we want to preserve, we want only constant blow up in communication, then this encoding needs to be only constant. And so with constant probability, it'll be flipped again. So we need this idea of doing kind of a local encoding won't work. We need a global mechanism of encoding. Okay, so let me now talk about previous work. There was also a lot of really beautiful work on this topic. So the first work is due to Schulman. That's in the paper that he proposed the problem. And in this work, he considered the random error model, so the stochastic noise. And he did show he got constant blow up in communication. And it was efficient in what's called the random string model, where the parties needed to share a long random string. So throughout the talk, I'm going to denote by n the communication, the number of bits communicated in the original protocol. Okay, so there's big N bits communicated in the original protocol, and we want to convert it to an error resilient protocol, where still we communicate at most order n bits. Okay, so that was the first work. And then came the second work of Schulman, where this kind of was a groundbreaking work, where this is where the notion of tree codes were introduced. And in this work, he did show constant rate and constant blow up in communication, resilient to constant fraction of adversarial noise. And he did this using a beautiful combinatorial object called tree codes. But the drawback of this work is that it required exponential blow up in computation. So in order to apply this thing, now Alice and Bob need to run exponential time to encode and exponential time to decode. Okay? And the only reason is because we don't have really good tree codes. So constructing a tree code that you can efficiently encode and decode are still lacking. So that's where the bottleneck is. Okay? And his error rate was 1 over 240, and then there was really beautiful work improving this error rate. This is of Breverman and Rao that improved it to 1/8 for the case where we send bits. For the case of large alphabet, it was 1/4, which is optimal. But again, it suffers the exponential time because they also use tree codes. So again, unless you have better tree codes, that's what you get. Okay. Then there was the work of Geles et al., where they managed to get efficiency. They managed to get efficiency, but only for random errors. And the way they got it is because they didn't use tree codes. So they used a weaker object called potent tree codes, which Ran mentioned in his talk. And potent tree codes, you can't do this thing, encode and decode efficiently, if in the case of random error. Okay, in the case of adversarial, it also works, but then again, it's inefficient. So again, exponential blow up. Okay? And then after that, there was a really nice work of Breverman that actually showed, he constructed a tree code in sub-exponential time. So now all the previous work that use tree code can actually do sub-exponential time because we have better tree codes. But until we have polynomial tree code that we can encode and decode polynomial time, you'll be stuck with inefficient encoding schemes. Okay, so what I'm going to show you today is how to get how to gain efficiency. Okay, despite the fact that we don't have efficient tree codes, we're going to show how to get efficient interactive coding schemes. Okay, and more generally, the way we do it is we give a general compiler, kind of a general way. Give me any interactive coding scheme that's inefficient, that there's a blow up of 2 to the n in the runtime, and I'm going to convert it into a polynomial-time error correcting code. So just give me any kind of way to encode with exponential blow up. I'm going to convert back to polynomial blow up. Okay, in efficiency. We do lose a little bit in the error rate. So if you give me interactive coding scheme that is resilient to eta error, then our interactive coding scheme is resilient to eta over 4 error. So we lose this constant fraction in resilience to error. Okay, I don't know if it's inherent, but that's what our analysis gave us. Okay, and another thing I want to note is that as opposed to previous constructions, the Schulman construction, the Breven-Monroe construction, our construction is randomized. So even if Alice and Baba in the original protocol, they were deterministic, now they have to use randomness. And so there's some probability of error that we fail. But this probability is exponentially small. Okay? So now to encode, we're going to use randomness to our advantage. And
isn't there always a probability of error?
no, if it's adversarial error, in the case of adversarial error, you know, I promise, in the random error there's always, because there's some probability that everything will error, but in the adversarial error there shouldn't be a probability of error. And like in Schulman's construction or Breven-Monroe, there's no probability of error for the adversarial case. But we have exponentially small probability of error. Okay, other questions? Okay, so, before I continue, I want to point out some follow-up work that happened after that, some of which I'm going to talk about more, I'm going to mention later on. So the first thing is this randomized business is annoying. Why do we need to flip coins in order to communicate? It doesn't seem necessary. So do we really need it to get efficiency or not? So in a work with Brakelski and O, we managed to get our construction. I'll mention a little bit how we did it, but to make it to not use randomness, but but instead we're going to make the simulator, the one that simulates, that makes the protocol resilient to error, he's going to be non-uniform. So what does it mean non-uniform? Essentially, we are using randomness, but it's once and for all, and we can fix it. So the adversary can know what it is. Okay, so it's kind of the non-uniform model. So think of it, okay, you choose n bits or order n bits, but it's fixed, everybody knows it, the adversary knows it, and you can use it from now on. Okay, so it's kind of a little bit of better than needing to flip coins all the time throughout every protocol, but it's still non-uniform, so it's not quite explicit. And then there's a very nice work of Yael et al. That Noga is going to talk about, which they managed to get really deterministic interactive coding with some caveats that Noga will say. Okay, so that's about getting deterministic. And then there was another work by Hoppler, which is very nice, and I'm going to mention that too. And what he did, his improvement, is that he got kind of the best communication blow-up possible, which is only if you want to be resilient to epsilon fraction of error, he blowed up the communication in the error resilient protocol only by order of square root epsilon, which is optimal. Okay? There's another nice features about this work, which I'm going to talk about towards the end of the talk. There was at the same time, well, I don't know, these all kind of appeared more or less at the same time. I think follow-up work to that. There was another very nice paper by Ghaffari and Hopler where they got optimal error rate and yet efficient. So kind of the Braverman-Rao work, but also efficient. They managed to make it efficient. And there was another work by Braverman and Klim Efremenko, who I think Klim is going to talk about tomorrow or something, which does interactive coding in the regime of list decoding. So all this, part of this you'll see later this week, and some I'm going to talk about later in my talk. OK, so now let's get to business. How are we going to, what I promised you, I told you, give me something inefficient, and I'm going to use it, but to make it efficient. How can I do that? OK, so here's a very, very simple idea. Inefficient. Why is it? It runs in time 2 to the n? No worries. Just run it in small chunks. So take chunks of size log n. OK, so you have a long protocol. And by the way, I'm assuming here, for simplicity, that in each round, each person sends 1 bit. It's kind of, this assumption is throughout all the works.
So inefficiency means that actually the protocol becomes longer. It doesn't mean that it's hard to compute it.
No, no. By efficiency, I mean it's computation. The time to compute is longer.
So actually, there is much more communication.
So in all the protocols, everybody insisted on blowing up the communication only by constant. Okay? So every time when we talk about interactive coding, the first requirement in all the previous work is that if you start with a protocol that requires n bits, the error-resilient protocol has only c times n bits. That's always. The question is, how long does it take you to generate these bits? So it's a computational question. Okay, so if originally, let's say, we did some computation, we talked back and forth, and I was a polynomial-time algorithm, and you are a polynomial-time algorithm. Now we run the error-resilient version. Do we need to become exponential time? So I want to say that we're still polynomial-time algorithm. So I want to preserve the computational efficiency of the players. Okay? So previous works, like Schulman's work, he preserved the communication but up to constant. He got error-resilient up to constant. The only thing that was missing there is the computation efficiency. So in his work, he needed to run all this in exponential time. And that's what I'm trying to improve on. Okay, I want it to remain efficient, to preserve the computational efficiency. Okay, so the first idea is just trivial. So look, I'm not starting from scratch. I'm starting, you give me something that's not efficient, that takes time exponential, 2 to the n. What am I going to do? I'm going to run it on log n bits. So I'm going to partition my algorithm to log n bits, log n bits, log n bits. Okay, I'm assuming here that each party just sends 1 bit at a time. Okay, it's kind of for simplicity. You can just assume that without loss of generality, but by making a lot of rounds. But this is mainly for simplicity, this assumption. So I partition to log n bits each chunk. And now what I'm going to do, I'm going to apply, give me any inefficient, computationally inefficient interactive coding scheme. And I'm just going to, Schulman, Braverman-Rao, whatever is out there, your favorite one. And I'm going to run it. This yellow in my talk is going to mean kind of in an error-resilient manner. Okay, this is the error-resilient algorithm. So adversarial. Oh, good. Yeah, I know. OK, so you're jumping ahead. So yes, the error are not random. They're adversarial. And I think already I'm getting kind of dirty looks saying, but what if all this is corrupted? I mean, you know, the adversary can corrupt this entire thing because he can corrupt constant fraction. And there's many more. This can be very long. OK, so this doesn't work. OK, so again, what was my original idea? Partition it to chunks of log n. Apply any non-efficient exponential time interactive coding scheme. So run this chunk, decode. Now I know I can find out that chunk. Now I can run the next chunk. In an encoding scheme, I decode. So now I know where we are in the first two. And that's how I'm going to run it. But it doesn't work. And the reason it doesn't work is because here I decode correctly only if there was some epsilon fraction of error, or eta, whatever I called it, some constant, 0.1 fraction of error. But now this entire thing can be corrupted. So there's no way I can decode, and there's no mechanism of kind of getting this back. Okay, so it's again the same problem that we had before when we said just apply standard error correcting code appears here. Nothing is really different. So this does not work. So it's not robust adversarial error. That's the problem. But we'll fix that, okay? So this will be fixed. So what's the second idea? So look, most of these will be fine because most of these will be able to decode correctly because the adversary can only put 0.1 fraction of error, so most of these will be okay. But some won't, and we need to somehow fix whatever is not good. So before we fix, we need to find out where the problem is. Once we find which chunks are problematic, we can hope to fix it. So how do we let's first find out which chunks are problematic. And here's how we do it. The idea is let's add consistency checks. So what do I mean? Let's run the chunk and then check. Are we okay so far? Are we consistent? Do we agree so far? So far so good kind of thing after every chunk. Okay, so after every chunk, we had a little test which kind of checks, are we good so far? Are we in agreement? Okay, and what is this? And this test is going to be very short, so it's going to be of size log n, so as not to blow up the communication. Okay, because each one of this is order log n, this is also going to be order log n. Okay, so how do we do this consistency check? Trivial, okay? The way we're going to do it, we're going to send some hash of our transcript. Okay, some function, just kind of some hash, some apply. For those who are not familiar with hash function, just in kind of a random function. Okay, you take your transcript so far. So now Bob, so far, this is just the consistency check part. What does he do? He has some transcript TB where he kind of recorded so far. They're in the middle of the protocol. He kind of thinks, okay, so far what I saw is TB. Alice also has a recording of her transcript, which is TA. Okay, the transcript of Alice. They want to make sure they have the same transcript in order to continue. How do they check? Yes, Anoop. This is the decoded transcript. Yes, thank you. Yes. So Alice and Bob, and each time they save the decoded, so they run this, they decode, and they save kind of the decoded transcript, the actual, this part, okay, what it decoded to. And then they check if they're okay. If they're okay, they continue. So they run this, they decode, and now they have, all of this. And so on, they continue. I denote by TA and TB the decoded transcripts corresponding to Alice and Bob. Okay, so each person kind of has kind of the decoding of which transcript he believes he read so far, he has so far. And now they want to make sure that they agree. Okay, so what do? They just apply a hash to the transcript. So Alice sends a hash, and Bob sends a hash of his transcript, so a hash function, a hash of his transcript. Alice sends a hash and a hash of her transcript, and they check if it's equal.
Why they send HP if they don't check?
So, okay, sorry. This Bob checks, the same thing Alice's checks. So this is only, I wrote it only from Bob's perspective. Alice does the same thing. So what Alice does, what Bob does, he gets this from Alice. He gets also the hash. There's a missing comma here. He gets the hash. He applies the hash to his transcript, and he checks if it's equal. Alice will do the exact same thing. She will take this and apply h of b to her transcript, and she will also check that it's equal.
But some error correction is made while doing this.
You can't be one slide ahead of me. And no, I'm joking. You're totally right. You're totally right. I'm going to get to that. That's a point. Good point. But let me first say before that point, so there was a good point that says, you can't just send this. What if the error can occur? It's not, you didn't do any error correction to it. I will do in a minute. But before I do the error correction, I just want to point out that we know how to do this, and I don't want to get into it, but there's a beautiful work of Alon et al. in Orno that they construct hash functions that the description of the hash is only order log n bits. The output of the hash is only order log n bits. And for a random hash, if these are not equal, then the probability that they will be different, so the probability that there's an error, namely that they're different, but you'll get a collision, you'll get equality, is only order 1 over n. Okay, so it's a very good hash that's efficient, and you catch errors with good probability. Okay, so So just know this can be, the communication here is order log n, and the probability of error is 1 over n, up to constants. Okay, so we're good with communication. But now again, as we said, we have to make this error resilient too, because otherwise it's enough that there's 1 bit of error and we're screwed. And we need to send all this log n bits over again or do some, so this has to be error resilient too. And the way we make it error resilient, I mean, there's 2 ways. You can just apply error correcting code to your hash, which is one way. We do it in a different way because it gets us better a bit better error parameter. So that's how we get the 1/4, only loss of 1/4, not more, is we take this consistency check and we apply the inefficient interactive coding scheme to all of this. So in other words, we, in our mind, think of here having consistency check, even if you don't need it, I mean, and now we apply the inefficient to this entire chunk. Okay, so this consistency check is going to be inside the interactive coding scheme. And each chunk like this is still order log n bits, because this was order log n and this was order log n. Okay? Questions? Yes?
You can still key one of these blocks, right?
You can kill one of these blocks. So this is our protocol. The only thing I didn't tell you, what do you do if there's an error? Okay? So you can still kill the block. But now at least, with some probability, we know that you killed the block. And if you don't catch, if I didn't catch you here, I will catch you here. So if we don't agree in a transcript, at some point, we're going to catch that we don't agree. And at that point, we're going to fix it. And what I didn't tell you is how we fix it. So that's going to be next. Any other questions? OK. So, OK, so how are we going to fix? How are we going to, what are we going to do? Let's say, like you said, the entire block can be wrong. And then we need to fix it. So this only I showed you, how can we find out that there was a problem? But now, what do we do if there's a problem? So here's an initial approach, OK? Here's what we do. Well, so check for consistency and what? So here's what. If it's consistent, then we're happy. We add, we say, OK, so we believe that we decoded. So I have here, you know, I had TA, you had TB. We're like happy. Yeah, it's the same TA, TB. I add my, I'm Alice, I'm a woman. I add my TA. I believe that's the correct thing. And I continue to the next chunk. That's if no error, I just continue, I'm happy. If they're not consistent, what do? So we did this, we decode. I said, wait, here the consistency check failed. So what do? I say, well, I'm not going to continue with this. This for sure is wrong because this was already wrong. And instead, what do? I say, you know what? Forget about probably there was an error in the previous chunk. Why would this be wrong? There was probably an error. And I'm going to forget about the previous chunk. I'm going to say, you know what? Forget about the previous chunk. I'm going to pretend, let's go back. Okay, and I assume you can go back as well, because I assume you also saw an error. So say, okay, we both probably saw an error. I'm going to go back to the previous chunk, and we're going to start the communication again. So let me do this pictorially. Okay, we start. I'm Alice. I hold nothing. My transcript is empty. Okay, this I'm always going to hold the transcript corresponding to the original protocol. Originally, it's empty. Okay, so the first consistency check, you don't need it. There's nothing to check consistency. It's empty. It's just here for kind of consistency. OK. Good. So we finished this. I got transcript 1. Hopefully, it's so nice. I'm, you know, a woman. You're all guys, so you can be my Bob. I'm going to be Alice. Sorry for that, too. Oh, 3. OK. You can, yeah, you guys are there. OK. So you're
changing the encoding through time?
I'm going to change the transcript that I hold. So we're talking. Originally, we didn't start. So our transcript is empty. We didn't talk yet. Now, we run the first part. We each decode. I got T1. Hopefully, you also got T1, because hopefully there were not too many errors. And then we continue. And we decode. Now, when we decode, we do a consistency check. Hopefully, the consistency check passed. If it passed, then, you know, and let's say it passed, we decoded, we got a new part. This is going to be T2. this is kind of the decoding of this chunk. Now my transcript is the concatenation, T1 and T2. I believe that this part decoded to T1, this part is decoding to T2, and everything is fine, hopefully. And now we continue, we run this. And if everything is fine, then we continue with T3. So here's an example. There were no errors. We just checked each time, and everything is good. This is the transcript corresponding to the original protocol. Good. I'm happy.
So every step you are checking along your transcript.
Exactly. Every check, I'm checking my TA versus your TB. And this grows. OK? Now, suppose there was an error. OK, so now suppose here was fine. But actually here, when we decoded, we thought T1 was fine, no error. But the T2, there's an error. Now, we don't know it yet, maybe. OK, maybe we think everything is fine because the consistency check passed. And I encoded T1. I decoded for T2, but you decoded for T2 prime. Now, we're going to run the next chunk. Here, we're going to notice, uh-oh, a problem. The consistency check failed. What we're going to do, we're going to assume, why did it fail? Because there was a problem here. And we're going to go back to this phase. So we're going to forget about this, because I'm going to realize probably T2 is wrong. I'm going to forget about this, and I'm going to go back to my T1. And now I'm going to run like this again, I'm going to run starting from point T1 of the original protocol. OK? And if the problem was earlier even, I'm going to slowly, slowly go up until I reach the problem. That's the idea. Yes?
So I guess the adversary cannot find collisions to this hash function, right?
OK. The adversary cannot find collisions to this hash function. Yes. OK, so here, I'm thinking here, the adversary does not know which hash. So at this point, this is fixed. Now, we're going to run the so now I have TA and you have TB. TA and TB are given to us. That's it. The adversary made as many errors as he wanted so far. Now I have TA, you have TB. Now, I send you hash. Now, either the adversary can ruin this altogether if he wants, but if he doesn't ruin this altogether, I send you the hash, you send me the hash, we check. There's nothing the adversary can do. Yes. However, later I'm going to show you that you actually don't. But for now, think of yes. You need fresh randomness every round. And when we wrote this work, we thought it's inherent. You must use fresh randomness every round. We thought of this as a big caveat, as a caveat, but actually I'll show you the analysis actually goes through even if you fix all the hashes ahead of time. But we'll get to that later. OK, so questions. OK, this is almost the protocol as is. But this doesn't quite work. There's a little bug. How am I on time? How long? Like I'm half an hour through or something? I don't know when we started. OK. Whatever. Tell me. OK, I don't really care. 15 minutes? How much? 20 minutes. OK. Good. I'm not that long time. OK, so this doesn't work. It almost works, but here's the problem. There's one problem here that can cause a failure. The problem is, what if we're not in the same chunk? What if I am, with T1, T2, T3, I think we're kind of on the third chunk of the original protocol. You think we're in the first chunk of the original protocol. And so we're never going to get into sync again. I have no mechanism of kind of syncing together. Now, one can think first, how can it happen that we're not in the same chunk? So let me show you an example. Suppose here, so here we're OK. I got T1, you got T, we decoded correctly, both of us. Here we didn't decode correctly. And now what can happen is the adversary can ruin this, invest order log n bits, so ruin this completely. And at the end of this, I think everything was fine. OK, so the hashes I got show no, everything. So the adversary completely corrupted Bob and tells me, don't worry, everything's OK. So I add my T3. And to Bob, he tells him, go back, everything, it's not OK. Now he went back. Now he's going to execute. He went back to round 1. So next round, he's going to execute the second chunk. I'm executing the fourth chunk. Now we're out of sync, and that's a big problem. OK? So the last ingredient of the protocol, and that's going to be the final protocol, is to fix this consistency check a little bit. We not enough to check that our hashes are the same. So, but we also need to check that we're on the same chunk, because it's not enough for both of us just to go back to the same point if there's a problem. We may need to kind of adjust our locations. Okay, so that's kind of the last ingredient. And the way we do it, I'm going to include my chunk number. Okay, so note the number of chunks is n over log n. Anyway, it's less than n, less the communication. So in order to encode a chunk number, it only requires log n bits. Log n bits I can afford. So I'm going to, in addition to sending my hash, I'm going to tell you, look, I'm in round 4. And you're going to tell me I'm in round 1, or whatever round you're on. Okay, and now let me explain. So our check is not, what we do if we find a problem is not as simple as it was last time. So I'm going to be a little more. Okay, so well, the reason we choose log n is, the reason we don't choose more than log n, it's a great question. The reason we don't choose more than log n is because then I'm going to be not going to be efficient, because I'm running on it a protocol of size 2 to the n, so I can use at most log n. Why we don't do less than log n, this is one very important reason, but at the end of the talk I'm going to mention a paper that gets around it and actually uses a chunk of constant size. So for us, yes, that was one of the reasons. For the hash we needed log n, which can also, turns out we can get around, and for this we needed log n. That's why we couldn't get smaller chunks. Okay? So we had to turn to this. Which round I am, it's log n. And now here's what I do. We decode. If everything's okay, the last one, if everything's okay, we're in the same chunk, no problem. What if there's a problem? What if we're not exactly okay? So we need to be careful. Now we do kind of case analysis. If I'm Alice, so if I'm on top of you, okay, I think we're up here, you think we're down there, I'm like, uh-oh, you're all the way down there, I'm going to wait for you to come up to me. I'm going to assume you realized also that you're in a way down, you continued on your own, I wasn't with you, I'm going to stay where I am. So I'm not going to do anything. Oh, sorry, I wrote here everything with respect to Bob. Okay, so here's what Bob does. If Bob is down, what he does, he goes up. He says, oh, I'm down, Alice is up there, I'm going to go back to her. So he just reduces one chunk up. He forgets about this, okay, forgets about this, and he goes, as before we said, he goes one chunk up. Not to IA, no. That's very important not to go to IA. Why? Because the adversary can corrupt this all together and tell them Alice is all the way in the top. Now, you can't go all the way to the top, because what if it was corrupted? Now you're doing all the protocol over again. So it's a very delicate thing, because you can never completely trust the transcript you get. So you need to be cautious. So you say, okay, there's a problem, but I'm not sure even if there's a problem. I think there's a problem, but I can't be even sure, because maybe the adversary just tells me there's a problem. So I'm going to try to get closer to you, but I'm not going to go all the way up if he tells me you're in the beginning of the protocol. So it's kind of I need to be cautious. Okay, so I just go one level up. If I'm all the way down, sorry, if IB is small, so now Bob is up, Alice is down. What Bob is going to do, Bob's going to do, you know, I'm just going to wait for Alice. She went all the way down. I'm up here. I'm going to wait for her to come up. So here, Bob he continues his own IB, his own chunk. He doesn't add this, because there's no point. This is wrong from his perspective. He's not going to add this. But he stays where he was before. Okay, he doesn't go. He's hoping that he'll stay here and Alice will kind of slowly go up to him. Okay? And if both of us are in the same chunk, but there was just a problem with the hashes, then they do as before. They both go up, okay, to kind of correct. So that's, if you didn't follow it, let me tell you, it's what you would do if you had to do it. It's the only logical thing to do. Okay, if you're all the way down, you go up. If you're all the way up, you wait for the other person to go up. If you're in the same place, you both kind of go back. So it's the natural thing. That's it. That's the protocol. Okay, so we just apply these consistency checks. We either continue or we go up. Sometimes I go up if we're not in the same chunk, and we kind of hopefully get together. The analysis. So let me first, I'm not going to show the full analysis because it's not complicated, but it's not that interesting either. It's pretty kind of just some work, but this straightforward thing kind of works. But let me give you the intuition for why this works. Okay? So the intuition is the following. I want to say that at every point in time, we're making progress. We're always making progress. Why are we making progress? Well, either the adversary, so let me put it, yeah. So think of the following. The adversary can ruin a chunk, but in order to ruin a chunk, he needs to invest a lot of error. So he needs to put like log n, order log n error to ruin a chunk, okay? Because he needs to at least constant, it's resilient to constant fraction of error. So he needs to invest some constant times log n in order to ruin a chunk. And he will need to continue to invest this log n error to not allow me to repair it. Okay, modulo, I'm leaving here the fact that there's some, in the analysis you also need to make sure that there's some randomness error, so there is a chance that the hash causes a problem, not the adversary. But, so that's, you can think of him as also some adversary, but that's where kind of randomness comes in. I'm going to leave this out. That needs to be incorporated. But leaving this out for a minute, just for simplicity, the idea is that the adversary, in order to cause for you not to make progress, the adversary needs to invest log n bits. Each time, each chunk. So now there's some kind of a win-win situation here. Either the adversary invested a lot of error, and in which case he's losing his budget, or we made progress. Okay, either we fixed something, which is progress, or we just we continued the protocol, which is progress. But either we made progress towards the end result, or the adversary had to invest log n bits of error, which kind of shrinks his budget by quite a bit. Okay, so we kind of, actually, the proof can be compressed. It's not really a proof, it's a quote unquote proof. But the proof goes, it's kind of a standard thing. We define this potential function, where the potential function is, it's log n time. So at any point in the protocol, there's the good rounds. The good rounds is kind of, G is the number of good rounds, so it's the number of rounds in which we're in agreement so far. We both agree that up to G, the transcript is T. Okay, so that's G is the good rounds. Alpha is the bad rounds that you believe that you also have, this transcript, but I don't. That's kind of bad because we'll need to correct that. It'll involve more time. So more good rounds, phi grows, kind of, you went without me in the protocol is bad, so we are going to pay for that. And, oh, I thought, okay. And E is going to be the number of errors. This is the resilience of error in the original the original interactive communication was resilient to tau error. The point is, it doesn't matter. The point is what we show is in every chunk, phi grows. The potential function grows by log n, except with small probability of error that it doesn't grow, but we bound that as well. Okay, but except for this random, the probability that of hash collisions, phi grows by log n, and so we show that after C n over log n rounds, the potential function is C times n. And if the potential function is C times n, we're in good shape, because what does it mean? It means that G log n, G is the good. We want to make sure that the G log n is at least big N, because that means that the number of good rounds is N over log N, and hence it's the entire communication. Okay? So if the potential function is at least Cn, the G log N, which is the number of bits that we agree on, is at least Cn minus this error. I don't want to go into it, but you can bound the error. He has a budget that's not too big, and then we need to do careful analysis. That's where the 1/4 comes in, that we lose 1/4 in order to make this small enough that we can kind of win the n. Nothing interesting goes on. It's regular kind of this potential function type analysis. But that's kind of the idea, main idea behind the proof. So okay, I just want to mention one thing. Note that we run this protocol for C n over log n chunks. Now you say, what do you mean? But what if you're done? What if you're done with the protocol? What do you continue with? Continue with zeros. Doesn't matter. So think of the protocol as really long as, you know, CN communication. The first n is what you want, and the rest are zeros. And then you just care about the first n bits. This is just to make it well-defined. Otherwise, when you're done, if you need to continue, you continue with what? So it's a padding kind of issue. But it's not important. OK. So just to summarize this part, so we got interactive coding scheme with the properties we wanted. It's resilient to constant fraction of adversarial error, just like the original computationally inefficient one, constant blow up in communication. And now we're efficient preserving because we apply the inefficient code only to log n size. So we run in time 2 to the log n, which is poly n. OK.
How do you preserve the probability of error being exponentially small?
OK, this will come up. OK, yeah, it's exponentially small. OK, the content I don't want to go into. But your question comes into I'll explain more in the deterministic construction. I'm going to only say a word about it. But let me answer your question. So each time there's an error with probability 1 over n, more or less. OK, 1 over c times n. And now what we show is, and this is an independent event. OK, so each time, look at all the places that were inconsistent, and the hash said we're consistent. That's the problem. We want to make sure that doesn't happen too much. That's an error in the hash. OK, we were inconsistent. We should figure it out, but the hash said we're consistent. OK, these events are independent. Each time we choose a random hash, and we check again and again. So we have here a bunch of independent events. What we show, as long as the number of bad times, so bad meaning there was a collision, is not too big, we're OK. And we essentially do a Chernoff bound. We show that it's a concentration bound. You know, we have n, or n over log n, experiment. You know, we run it n times independently. Each time there's some, you know, only 1 over n probability of error, and we want to make sure there's not too much. We just do a standard Chernoff bound. OK. So I'm not going to say much about the deterministic approach. I just want to say that where was the randomness? The only place we use randomness is for this hash function. That's the only place we use randomness. We choose randomness hash function at random. That's why our simulator, our error-resilient protocol becomes randomized. And what we show is, and that's very counterintuitive in the beginning, we don't know how to get rid of it altogether, but what we show is we can just send all these hashes ahead of time. And moreover, once and for all the protocols. OK, you can fix this hash, so choose them once, fix them, the adversary can see them, it's fixed, and with very, very high probability, not over the adversary, over the hash. So with all but exponentially small probability, it's going to be OK. And it sounds very counterintuitive in the beginning, but I want to tell you why this happens in a little bit. I won't have time to give you the details, but just the idea. The reason is that, so this is kind of the observation. The observation why you can send the hashes ahead of time and the adversary can't kill you, because he can be dependent on these hashes. The reason he cannot, it's OK, is because at any point, so the adversary can kill, so we're in some point in the execution. The adversary can kill the next chunk, OK? But there's not that many things. He can only kill, what can he do? He can only make you add a chunk. So for the next round, what can he do? He can either make you add this chunk, in which case he has total, you know, there's log n bits. He can choose which log n bits he wants you to add. So it's n options. Or he can make you delete a chunk or wait. So at any point, the adversary can make you do only n plus 2 things. He can, it seems like, so when we run this hash function over and over again, we run it on a transcript of size more or less n. It would start small, but very soon it becomes n. So it seems like we run it on any transcript of size n times. Like, so there's kind of n squared options to run it on. But that's not true. there's only, it's not 2 to the n squared, it's only 2 to the n. And that's kind of what saves us. So what do I mean by there's only 2 to the n? So fix the input x and y, okay? The adversary can cause us to run to compute the hash function. We compute the hash function about n times, n over log n times, throughout the protocol. Because the protocol is of length n, it seems like we have many, many options. Each time we have 2 to the n options, 2 to the n to the power, and we do it n times, 2 to the n to the n, it seems like 2 to the n squared. But at any point in time, the adversary actually, there's only n plus 2 options of changing the protocol, so the transcript so far. So in the beginning, I either add my log n bits or I don't. The adversary, let's say, has total control. He chooses. Okay, n options. Next step. Either I add log n bits, or I delete, or I go back up. So delete one option, go back up one option, or add, he can make me add whatever n options, n plus 2 options. N plus 2, n plus 2. The overall, there's at most n plus 2 times the number of chunks, transcripts, that ever I'm going to send to this hash function. And the adversary has no control over that. I'm enumerating over all possible ways the adversary can behave. Okay? And now, what I need, I want to say if I choose a random hash function, so a random hash is for all the rounds, I choose a bunch of hash functions, I want to say that with overwhelming probability on this hash, I want to say the number of collisions is going to be small. No matter how, because there are so few transcripts, I'm going to get the probability of error is exponentially small. And it's exponentially small, I can also enumerate over x and y's, and I get exponentially small. So I didn't really show you the details, but this is kind of the key observation, that we're not, that at any point there's only polynomial many options, not exponentially many options. So, okay. I want to end by just mentioning in one word the work of Hopler, the follow-up work of Hopler, and that goes back to Amos's question. So note that we had consistency checks of size log n, and that's why we needed to use, and we said that here we encoded using the inefficient coding scheme. So we use tree codes of depth log n, which is efficient. It's small enough, it's okay. But turns out, and this is kind of an amazing observation, you don't need tree codes altogether. So for a long time, we felt like tree codes or potent tree codes, that's inherent to do. It seemed like kind of one and the same, that you have to have it to do, you have to have some kind of tree codes to do interactive communication. It turns out, no, we don't need it at all. And what Hopler showed, he said, you know what? Exactly Amos's question. Why are you doing log n here? Why don't you just do order 1? Just do order 1. And now you don't forget, you don't need to encode this. Just do consistency check each time. So send constant number of bits, check. Send constant number of bits, check. Do the same thing, but why encode? If there was a problem, go back. Anyway, you only paid a constant. And it works. The only thing is that it seems very easy, but it turns out it's really complicated, because how do you do that? Now you have only constant number of bits for the check. How do you do it in constant number of bits? So, okay, for the hash, you just output constant number of bits of the hash, and it works pretty easily. That's not a problem. This hash is also very big. It's log n. So what do you do with that? Well, he has some de-randomization tricks. That also works pretty well. I mean, easily kind of thing. You would expect this is kind of exercise. But the round, how do we send which round we're on? No way, I can't send it. And so he doesn't really send the round. He can't. So he does much clever, a lot of, it's complicated. He gets around this in a very complicated way, but it works. No tree codes. So, kind of, but not quite. Yeah, but that's what you would want, but it doesn't quite work, so it gets much more complicated than that. But that's kind of the first idea, exactly. Okay. Oh, and the big bonus for his work is that he gets optimal communication rate. So he blows up that was kind of maybe his original motivation. He blows up the communication by order of square root epsilon. Okay, so let me just conclude. So we got good interactive coding scheme with constant blow-up in communication, resilient constant error, and computationally efficient. Thank you very much.